Okay, this is going to be part 3 of the video on the limit comparison test, and this is what the test looks like right here. And I'm going to assume now that you've watched the first 2 videos, and it will be important that you do because it will have an effect on what goes on in this video. Now in this video, what we're going to concentrate on is helping you figure out what to pick for the test series. And it won't take you long to figure out if you have an original series and you want to compare it to a test series. What you pick for the test series is very important, but how do you pick it? So to start with, we'll look at an example from the previous problem. Let's go to that. Now again, this is the first example that we worked in the previous video. And if you haven't done it, definitely watch it because it'll show you step by step how all this came about. But we'll kind of run through it a little bit right here too. Now, let's look at a couple possibilities. The idea is that you're given this original sequence and you want to come up with a test sequence to model it. Well, what we talked about in the first video is if you just concentrate on the dominant terms, a lot of times that'll give you a good idea what the test series should look like. But the question that some students have, and I think I'll emphasize it right here, when you look at the dominant terms, should you include the leading coefficients or not? And let's take a look at what difference it makes if you do include them or you don't. So the idea, if I wanted to concentrate on the dominant terms, it would be, I think I'll put a little box around them, it would be these leading dominant terms right here. So if you use this, then 3n squared over 2 to the 5th, and use this as the basis of your test series, that's a very good choice. Now the reason it's a very good choice is if you look at the original one, the original series behaves like n squared over n to the 5th, which will behave like 1 over n cubed, because 2 in the top cancel out 2 in the bottom leaves it. So the original series is going to behave something like this. So if you can come up with a test series that has the same behavior, then you're off to a good start. But in this case, let's suppose we have 2 students. This first student decides to include the leading coefficients, then we'll rework the same problem with a student who decides not to include the leading coefficients and see what difference that makes. Now again, this is what we did in the last video, so nothing new here, we'll just run through it again. So this was your test series. The n simplified, and it simplifies down to 3 over 2 to the n cubed power. Now this is important because the order of magnitude of the original series and the test series are both n cubed. Now the next step, of course, is you've got a test series. You need to know, does it converge or diverge? And what you did in the last video, 3/2 is a constant, so you pulled it out in front. This is a p series with p equal to 3. And you know from previous work that if the p is greater than 1, that the series converges. So you can show that even with these leading coefficients, the test series does converge. So then you took the test series and you found the ratio. The original function divided by the test function, but I'm going to highlight the coefficients in this. Here was 3/2. Here, this student included the leading coefficients and had a 3/2. They show up right here as 3/2. You can pull them out in front as you find whether the test series converges or not, but you still got them. Now, when you did your ratio test, notice here is the 3/2 that shows up right here in the test series. When you invert and multiply, now the 3/2 becomes a 2/3, but it goes right here. Now, the effect of including the coefficients, watch this, when you multiply them, 2 times 3, this thing turned into a 6. In the bottom, 2 times 3, this turns into a 6. So what including the leading coefficients has the effect of doing is that it changes in the final expression. It will turn both the same thing. So you've got 6 divided by 6. As you go way off to infinity, 6 divided by 6 gives you 1 over 1, and you came out with this. The ratio of the original series to the test series was 1 over 1. And from that, since it turned into a fixed positive number, using the rule, if the ratio is a positive fixed number, if the test series converged, then the original series converged, and you were able to show that this thing's true. So that's the whole first problem. Nothing special there. Now let's do one thing that we didn't do before, though. Let's make a quick graph and see what this looks like. What does it mean for the ratio to be equal to 1? And I think I'll come over here and do it this way. I'll draw a quick little graph. So as I go way off to infinity, if I were to plot the points of this test sequence, and suppose they look something like this. Now I know that they converge, so they have to be approaching 0, has to look something like that. So that's the test thing. Now, if the ratio is 1, think of that as 1 over 1, that means that all the terms of the original sequence have the same height as the test sequence. So now if I were to plot the terms of the test sequence, and this is if you go way off to a positive infinity here, that the terms of the original sequence will be exactly the same height. If the original sequence is this high, then the test sequence is also that high. They have the same height, and these two behave exactly the same. So you're able to conclude if the red dots converge, then the blue dots must also converge because the ratio is the same, and in this case, they happen to be the same height. Now, keep that in mind. So once again, if you decide to include the leading coefficients in your test series, then later on, when you evaluate the ratio, it will change from, since you've got a 3/2 on the top and a 3/2 on the bottom, they will both change into the same coefficients, and you'll get a 1. So if you include the leading coefficients, eventually the original series will behave and converge at exactly the same rate that the test series did. Now, let's compare that to a student who elected, same choice, but elected not to include the leading coefficients. And so we'll run through the same thing again. Okay. Now what you've got is something that looks like this. Now, the only difference is, rather than including the 3 and the 2, we're just going to include the n terms. And this, by the way, is also a perfectly good choice. It's still based on the fact that the original behaves like 1 over n cubed. But let's see what it would look like. So now, if you elected not to include the 3 and the 2, then this would be gone, and this would be gone. When you simplify this 3 would now be a 1, and this one wouldn't be here. So you'd have 1 over n cubed. This ratio wouldn't be here. You'd have this, but you still, even if you picked it to be 1 over n cubed and elected not to include the leading coefficients, the test series still converges. Not a problem. Now, let's see what effect it has down here. Again, if you didn't include this, now your test series, rather than being 3/2 of 1 over n cubed, it's just going to be 1 over n cubed. So this 3 is now a 1, and this thing doesn't exist. When you invert and multiply, the 2 doesn't exist, and the 3 is now a 1. Now, when you distribute, this time you'd get this. Rather than getting 2 times 3, which was 6, you're going to get 1 times 3. Rather than being a 6, this leading coefficient is going to be a 3. 1 times 2, rather than being a 6, this leading coefficient is going to be a 2. So it's going to look like that. Now, in this case, if you take the limit as n goes off to infinity, the power in the numerator is the same as the power in the denominator. So this thing the limit will actually be the value of the leading coefficients. It'll turn out to be 3/2. Now, is this a problem? No. 3/2 is still a fixed positive number. So a fixed positive number. And what that means is, even though it's, now in the first one, if you included the leading coefficients, you got 1. If you do not include the leading coefficients, you get a limit of 3/2. But it's still good. The original series still converges. So I guess kind of the moral of the story here is this, is when you're working with dominant terms, it's your choice whether you include the leading coefficients or not. The first student elected to include them and came up with a ratio of 1, but that's just fine, it works. The second student elected not to include them and came up with a different ratio, but it's still a fixed positive number, it works just fine. So either one of those choices are okay. Now where it'll show up different, let's do this graph thing again, and it'll look a little different on the graph as you graph them. So what does it mean for this second one to have 3/2? Well, again, we'll go way off here toward a positive infinity. Now let's graph the test case. The test case is 1 over 2/3, and I know it converges, so the test series is going to look something like this. The sequence that makes up the series. It looks like this. Now, when the ratio was 1, the original series dots had exactly the same height. But in this case, the ratio is 3/2 or 1.5. So what this means is that each one of the terms of the original series is 1.5 times the height of this one. So if this height was 1, 1.5 would put you up to about right here. If this height was whatever it is, if you multiply it by 1.5, it'll be up to, say, about right here. This height would get you up to about right here. This height, 1.5, gets you to about right here. This height, 1.5, gets you to here. 1.5 gets you to here, and so on. So the idea is, in this case, if this height is 2, then this height would be 3. But if the red dots are converging, then so are the blue dots. So again, and the important thing here, we'll go back to this, that you picked the order of magnitude of the original series was n cubed. The order of magnitude of the test series was n cubed, and that's the important thing. As long as you get the order of magnitude right, coefficients aren't going to have any effect on it. They will have an effect on what the limit is, the ratio is, but ultimately, having a fixed ratio of 1 is just as good as having a fixed ratio of 1.5 because they're both positive and you can show that it converges. So student 1, student 2 made a good choice. Now let's take a look at students 3 and 4 who make a bad choice. So how do you make a mistake on this? So far, now the rule says this. The rule says, and we'll go back up to the top here, the rule says that it has to approach a fixed positive number L. But what would happen if you either got an infinity or a 0? Let's take a look at where a situation like that might come from. So we'll go down here to example number 3. And we'll do this. So in this example, now what I'm going to do here is I'm going to kind of do the same thing. I'll keep the leading coefficients and I'll look at the dominant terms. And this happens occasionally. Suppose that you make, as a student, you make a mistake. So this thing is going to behave just like the other ones did, as if it's a 1 over n cubed. Now suppose you came across here and you did this. You set it up and you decide to work with the dominant terms. You go through this, but let's suppose you made a mistake. Rather than coming up with n cubed, you came up with n to the 4th here. So this becomes n to the 4th here. Now this is going to have some big effects. The idea is it's extremely important whether the order of magnitude of the original series agrees with this. If they do, they'll behave the same. But if you have an n to the 4th, you've got a test series that's a completely different order of magnitude of the original series. And watch what effect that has. Now, first of all, if you come over here, it's still a p series. P is still greater than 1. Even though it's n to the 4th, the series still converges. Not a problem. But watch what happens when you plug it in down here. So if you made a mistake here, and this thing turned out to be an n to the 4th, then when you invert it, this one right here is going to be an n to the 4th. When you multiply it through, you'd have a 6. Now, add the exponents, 2 plus 4, this is now an n to the 6th. And so if you find the limit, now if the power in the numerator is greater than the power in the denominator, no matter what the coefficients are, if you go off, this thing is going to go off to infinity. So now the limit is infinity, and what this means is none of this is true. It's not a fixed positive number, and you can't conclude that this thing converges. So in this case, the test fails. The comparison test fails. Fails. So the comparison test fails. Now, it's not that the test fails, it was that you made a very poor choice of a test sequence. So for the limit comparison test to have any chance of working, the order of magnitude of the test series has to agree with the order of magnitude of the original series. Coefficients don't matter. You can keep the coefficients or not. It's the powers that make a difference. Now, in this case, we made a mistake and got a test series that had a power that was too big. So let's do one more and make the same mistake, but this time let's come up with a test series that's too small. So what I'll do is exactly the same thing, starting with this. I'll go through this, and suppose you did this, but rather than having n cubed, suppose this time you made a mistake and came up with n squared. Now again, p is still greater than this. Even though it's n squared, it's wrong. This series still converges. And this one is behaves like 1 over n cubed. So again, n squared is not going to behave like n cubed, but let's see what effect that would have over here. So down here, this one is now, rather than n cubed, it's now n squared. When you invert and multiply, this one is now n squared. When you distribute this, you've got an n squared times an n squared. This thing now becomes an n to the 4th. When you take the limit, if the power in the numerator is less than the power in the denominator, then no matter what the coefficients are, this entire thing is going to go to 0. And that's going to be L. But again, the limit has to be a fixed positive number. It has to be greater than 0 and a fixed number. And what this means is, again, the test failed. So the test is going to fail. And that means you can't conclude this, and you can't conclude that the series converges. And again, not because it's a bad test, but because you made a bad choice of your power. This thing right here would be squared. So you just made a bad choice. So let's kind of run through all of these again. First of all, if the order of magnitude of the test series is not the same as the order of magnitude of the original series, then you're going to have trouble. But it's also true, let's go back up to our first examples, if you get the order of magnitude right, if it's 1 over n cubed and you've got a 1 over n cubed, it doesn't make any difference whether you include the coefficients or not. If you elect to include the coefficients, then eventually they'll cancel out and the ratio is going to be 1. If you don't include the coefficients, let's take a look at that second example. If you don't include the coefficients, then when you find the ratio, it'll turn out to be a different number. And as a matter of fact, you might notice this. The limit of this thing was 3/2. And in this case, we'll go up to here. It's no accident that that exactly agrees with the leading coefficients. Because if you've got leading coefficients right here, and there's nothing down here to cancel them out, they'll carry all the way through, and they'll show up right here. So just a little heads up for you. Okay, so anyway, hopefully what this does, it makes it a little bit clearer of what to pick for this test series. And again, say it again, it's your choice. If you want to include the coefficients, great. If you don't want to include the coefficients, great. But what you can't do, you can't make a mistake on the order of magnitude. As long as you got the order of magnitude right, you're going to do okay. So if the original series behaves like a 1 over n cubed, then your test series had also better behave like a 1 over n cubed. If it's something else, this isn't going to work.